You think light travels in straight lines. You've been told this your whole life. Draw a line from the sun to your eye. That's the path light takes, right? Simple, direct, obvious. Except it's completely wrong. Light doesn't take a path. It takes every path. All of them. Simultaneously. And here's the thing that'll really mess with your head. Light somehow knows about barriers and obstacles that aren't even in its way. It makes decisions that seem impossible. As if it's exploring the entire universe before choosing where to go. This isn't philosophy. This isn't speculation. This is what actually happens. And we can prove it in a laboratory. Richard Feynman spent years unraveling this mystery, and what he discovered changed everything we thought we knew about reality itself. Let me tell you what's really going on when light travels from one place to another. Start with something simple. You're sitting in a dark room, and someone turns on a lamp across from you. Light leaves that bulb and reaches your eye. How did it get there? You'd say it traveled in a straight line, and you'd be mostly right, but only because you're not looking closely enough. Now let's do an experiment. Put a mirror between you and the lamp. Angled just right. The light bounces off the mirror and reaches your eye. You see the lamp's reflection. Ask yourself, what path did the light take? It went from the lamp to the mirror, then from the mirror to your eye. The angle coming in equals the angle going out. That's the law of reflection, something you learned in school. But here's the question nobody asks. How does the light know to hit the mirror at exactly that spot? Think about it. The light leaves the lamp going in all directions. Some of it hits the mirror near the top, some near the bottom, some right in the middle. But only the light that hits one particular spot, the spot where the angles match, actually makes it to your eye. Why that spot? What's special about it? The standard answer is that light takes the shortest path, or the fastest path, or the path where angles equal each other. But these are just descriptions of what happens. They're not explanations. They don't tell you why. Feynman asked a different question. He asked, what if light doesn't choose a path at all? What if it takes every possible path, and we only see the result of all those paths added together? Sounds crazy, right? How can light take every path? How can a photon leaving that lamp somehow travel along millions of different routes, straight paths, curved paths, zigzagging paths, paths that loop around the room 3 times all at once? Let me show you why this isn't just possible, but necessary. Go back to that mirror experiment, but now let's cover up different parts of the mirror and see what happens. Cover the top half, you still see the reflection. Cover the bottom half, still see it. Cover everything except one tiny spot in the middle where the angles match perfectly, and you still see the reflection, just dimmer. But here's where it gets strange. Cover up that perfect spot and leave everything else open. What happens? The reflection gets dimmer, but it's still there. Light is reaching your eye from parts of the mirror that shouldn't contribute according to the simple angle matching rule. Now cover the mirror with a series of thin stripes like vertical blinds alternating between covered and open. What you see depends on how wide you make those stripes. Make them wide enough and the reflection looks normal, just dimmer. Make them narrower and weird things start to happen. The reflection might get brighter in some places and disappear in others. Move the pattern slightly and everything changes. This is impossible if light is taking just one path. This is impossible if light knows where it's supposed to go and goes there directly. What's happening is that light is taking all the paths, every single one, and those paths are interfering with each other. Feynman explained this in his lectures on quantum electrodynamics. And what he showed us is beautiful and terrible at the same time. Every photon that leaves that lamp explores every possible route to your eye. Not metaphorically, not approximately, Actually, each path contributes something called a probability amplitude. Think of it like a little arrow spinning around as the light travels. The arrow spins at a rate that depends on how long the path takes. A short path, the arrow doesn't spin much. A long path, the arrow spins around many times. When you add up all these spinning arrows from all the paths, something remarkable happens. Most of them point in random directions and cancel each other out. But paths that take about the same amount of time, their arrows point in roughly the same direction. They add together instead of canceling. And guess what? The paths that take about the same time are exactly the ones clustered around that special path where the angles match. That's why it looks like light takes the shortest path. It's not that light chooses that path. It's that all the nearby paths add up constructively while the faraway paths cancel out. This is the principle of least time, but now we understand what it means. It's not a rule light follows. It's a consequence of light following no rules except take every path and add up the amplitudes. Now let's push this further. Let's ask why this happens. Why does nature work this way? Think about what it means for light to know which path to take. If you put up a barrier somewhere, blocking certain paths, the light has to respond to that barrier even before it gets there. How? The light leaving the lamp hasn't reached the barrier yet, so how does it know the barrier exists? The answer is, it doesn't need to know. It tries all the paths, including the ones the barrier blocks. But when you add up the amplitudes, the blocked paths contribute 0. They're simply not there in the final sum. The light doesn't need to know about the barrier in advance because it's not making a decision. It's exploring all possibilities simultaneously, and reality emerges from the sum. This is what Feynman meant when he said nature uses the path integral formulation. You don't calculate where light will go by finding the right path. You calculate it by summing over all paths, each weighted by its probability amplitude. Every photon is in some sense everywhere at once until it arrives. It's not that we don't know which path it took. It's that asking which path did it take is the wrong question. The photon took all of them. Now here's where your brain should start hurting. Let's talk about the double slit experiment, the most famous demonstration of this quantum weirdness. Set up a barrier with 2 narrow slits cut in it. Shine light at the barrier and look at the pattern on a screen behind it. What do you see? Not 2 bright lines corresponding to the 2 slits. You see an interference pattern, alternating bright and dark bands. Why? Because light going through the left slit and light going through the right slit are both reaching each point on the screen, and their probability amplitudes are adding together, where they add constructively bright band, where they cancel dark band. But here's the part that destroys your intuition. Send light through 1 photon at a time, so dim that only 1 photon exists in the apparatus at any moment. Wait for it to hit the screen, record where it lands, then send another one. Build up the pattern 1 photon at a time. What happens? The interference pattern still appears, 1 photon at a time over hours or days, and the pattern emerges. Each photon is interfering with itself. There's no other photon to interfere with. It's going through both slits simultaneously, taking every possible path from the source to the screen and interfering with itself along the way. Close 1 slit. The interference pattern disappears, not because you're blocking half the light. That would just make everything dimmer. It disappears because you've eliminated half the paths, and without paths going through both slits, there's nothing to interfere. Now comes the really disturbing part. Put a detector at each slit to see which one each photon goes through. Just watch which slit it uses without blocking anything. The interference pattern disappears. Just by observing, by measuring which path the photon takes, you've changed the outcome. The photon, which was taking both paths when you weren't looking, now takes 1 path when you measure it. The wave of probability collapses into a definite outcome. Feynman called this the central mystery of quantum mechanics, and he was right. Light seems to know whether you're watching. It behaves differently depending on whether you measure its path. And nobody, not Feynman, not Einstein, not anyone, has a comfortable explanation for why. But here's what Feynman did explain: the mathematics of it, the precise rules governing how probability amplitudes combine, the path integral approach that lets you calculate exactly what will happen in any experimental setup. According to this approach, every possible history of the photon contributes to what actually happens. The photon going through the left slit is one history. The photon going through the right slit is another history. When you're not measuring which slit it goes through, both histories contribute and they interfere. When you measure, you force the photon into one definite history, and interference disappears because there's only one history now, not a superposition. This applies to everything, not just light. Electrons do it. Atoms do it. In principle, even baseballs and planets do it, though the interference effects become impossibly tiny for large objects. You, yes, you are a quantum object. Right now, your body is taking every possible path through space-time. The version of you sitting here, the version shifted one atom to the left, the version vibrating slightly differently, all these histories are happening simultaneously, and they're interfering with each other. But the interference effects for something as massive and complex as a human body cancel out almost perfectly. The sum over pairs gives you one definite classical trajectory because all the quantum wiggles average out. For a photon, though, those wiggles don't average out. A photon is light enough, simple enough, that the quantum nature stays visible. You can see the interference. You can see it taking multiple paths. And this leads to something profound. The path of least time isn't a rule light follows. It's a consequence of quantum mechanics. Classical physics, the physics of definite paths and predictable trajectories, emerges from quantum physics when you sum over enough paths that the weird stuff cancels out. Feynman showed us that you can derive all of classical physics from this quantum path integral approach. Newton's laws, Maxwell's equations, everything. They're all approximations that work when quantum effects wash out. But the fundamental description is quantum. Light taking every path, particles existing in superposition, probability amplitudes spinning through complex space. Let's connect this to the rest of physics. Why does light behave this way? What determines the rate at which those probability arrows spin? The answer is action. In physics, action is a quantity defined for each path, depending on the energy and time involved. For any path light might take, you can calculate its action. The rule is simple and beautiful. The probability amplitude for each path is determined by its action. Paths with similar actions have their amplitudes add up. Paths with very different actions cancel out. And the path that classical physics predicts, the path of least time, is the one where the action is stationary. It's the path where tiny variations don't change the action much, which means nearby paths have similar actions and add up constructively. This is the principle of least action, one of the deepest principles in all of physics. Feynman's path integral formulation shows that it's not an independent law, it's a consequence of quantum mechanics and the summation over all possible paths. Every force, every interaction, every phenomenon in physics can be described in terms of action in path integrals. Gravity, electromagnetism, the nuclear forces, all of them. Feynman himself used this approach to develop quantum electrodynamics, the theory of how light and matter interact, which earned him the Nobel Prize. But here's what makes this so strange and wonderful. The principle of least action looks like a statement about purpose. Light takes the path of least time as if it's trying to minimize something, as if nature is optimizing. But Feynman showed us that's an illusion. Nature isn't optimizing anything. Nature is doing everything. All paths, all possibilities, all histories. We see optimization because when you sum over all possibilities, the stationary path emerges naturally from the mathematics. There's no intelligence behind it, no decision-making, just the blind mechanical addition of probability amplitudes according to a simple rule. And from that simple rule, all the complexity and apparent purposefulness of the physical world emerges. Think about what this means. Every time you flip a light switch, you're triggering a process where trillions of photons explore every possible path between the bulb and your eye. They're going through the walls, looping around the room, taking detours through other galaxies, all of it. And somehow, when you add up all those impossible paths, you get the simple, predictable beam of light you see. The universe is far stranger than we imagine. It's not just that we don't know which path the photon takes, it's that the question itself is wrong. The photon doesn't take a path, it takes all paths. In reality, the definite solid world you see around you is the emergent result of endless quantum possibilities interfering with each other. Feynman loved this. He spent his entire career exploring the implications of this quantum weirdness. And what he found over and over was that when you stop trying to force quantum mechanics to make intuitive sense and instead just follow the mathematics, the universe reveals itself to be far more beautiful and far more strange than any story we could make up. Here's the final piece. The next time you see light streaming through a window, or reflecting off water, or making rainbows in the mist, remember what's really happening. Those photons aren't following simple paths. They're exploring the entire universe, taking every route simultaneously, interfering with themselves in ways that produce the patterns you see. You're not seeing light travel. You're seeing the result of light having traveled every possible way at once. And that's not a metaphor. That's not an interpretation. That's what actually happens, according to our best understanding of quantum mechanics. Feynman proved it mathematically. Experiments confirm it. This is the real nature of light. The universe is quantum all the way down. Classical physics, with its definite positions and predictable paths, is the approximation. Quantum mechanics, with its superpositions and path integrals, is the reality. And once you accept that, once you let go of the idea that things have to make intuitive sense, you start to see the universe as it truly is. Not a clockwork machine following predetermined rules, but a vast, shimmering web of possibilities, all happening at once, interfering and combining to create the reality we experience. Feynman knew this. He understood it better than almost anyone. And he spent his life trying to share that understanding, to help people see past their classical intuitions and glimpse the quantum reality beneath. Light doesn't choose its path, it takes every path. And in that simple, strange fact lies one of the deepest mysteries of existence, a mystery that we've learned to calculate with incredible precision, but that nobody can fully explain. That's the beauty of physics. We don't need to understand why nature works this way. We just need to describe how it works, to find the mathematical rules that predict what will happen. And Feynman gave us those rules: the path integral formulation, the sum over histories, the probability amplitude spinning through complex space. These aren't easy ideas. They take time to sink in. But once they do, once you truly grasp what it means for light to take every path, for particles to exist in superposition, for reality to emerge from quantum interference, once you see that, you can never unsee it. The world becomes richer. More mysterious. More wonderful. And you realize that the simple act of light traveling from a lamp to your eye is actually one of the most profound phenomena in the universe. A window into the quantum nature of reality. A demonstration that the world is not what it seems. Feynman knew why light behaves so strangely. He worked out the mathematics, developed the theory, made the predictions that experiments confirmed, and he tried to share that knowledge, to help others see what he saw. This is what he saw: a universe where nothing follows a single path, where everything exists in superposition, where reality is woven from probability and interference. A universe far stranger and far more beautiful than we ever imagined. That's the universe we live in. That's the world revealed by quantum mechanics. And every beam of light, every photon reaching your eye is proof of it. Something strange happens when light chooses its path. But Feynman showed us it's even stranger than that. Light doesn't choose at all. It does everything. And somehow, impossibly, that everything adds up to the one thing we see.